Okay, so next up is other trusted computing technologies, the things that, basically the rest of the infrastructure. Now, there's a heck of a lot out there in terms of other trusted computing technologies. I could probably spend an entire day just on the various things the TCG is doing. I'm not going to, for a couple of reasons. One of which is it's way too long, and a lot of it is still very up in the air. And frankly, it's not my area of expertise. So what we will be covering here, so we're going to be covering the roots of trust for measurement, which this phrase keeps cropping up and cropping up and cropping up. Now we're going to tell you what they are and how they work, because these are really, really important. We're also going to talk a little bit about Trusted Network Connect, because it is probably the best known of the trusted computing applications out there. It's the one that you can actually go to a store and you will find routers that say things like, "We support Trusted Network Connect." It's the only trusted computing application that you have any chance whatsoever today to just go out and buy. That said, how useful that is a little dubious, and we'll get to why shortly. And then I will touch at least a little bit on what else is out there, but we're not going to go into a whole lot of detail. So, why on earth? I'm sorry, guys, I don't know why this keeps popping up. Tooltips. I don't. Yeah. So, the core concept that we're going to be building on with this whole root of trust for measurement thing is the idea of a chain of trust. The idea here is that I have some component A, which measures component B, and stores that measurement. Component A then basically hands off control to component B. Component B now says, all right, I can measure some component C and store that measurement. Hands off control to C, C measures D, stores that measurement. So now I have a verifier who can say, if I trust A, then I trust A to have measured B correctly. By which I mean that measurement means something, and that the B that it handed off control to is the one that it measured. So when I say accurate measurements, that's generally what I mean, is it at least reflects the state of what started. So now I can look at that measurement and decide, do I trust B? If I trust B, then I can trust that it measured C correctly and evaluate that measurement. So I can start from a root and build up to potentially a pretty long chain of I trust A, so I trust B. I trust B, so I trust C. I trust C, so I trust D. And at every single step of the way, I'm actually checking a measurement. So I'm not blindingly trusting anything except that root. So there are two potential roots of trust for measurement. The static root of trust for measurement is part of the BIOS. It's BIOS boot block, I believe. It runs automatically as part of the system boot. If you turn the TPM on and you boot your machine, it will have measurements in it. And the reason it has measurements in it is the static root of trust will always just go. It's used to create the boot time chain of trust. So when the BIOS boots, the BIOS boot block boots up, measures the rest of the BIOS. Hands off control of the rest of the BIOS. The rest of the BIOS measures the bootloader in two different pieces, hands off control, and so forth. There's also a dynamic root of trust for measurement. This is part of the CPU. This is that TXT or SVM thing. The dynamic root of trust for measurement itself is a piece of signed code for the manufacturer. It is not run by default. You have to enter it deliberately. I run a command that's called sender in the Intel world. I'll be honest, I don't know what it's called in the AMD world. And that turns on a special secure CPU mode in which nothing else is executing except this little piece of trusted code. And we can use this to create what's called a late launch chain of trust. And part of the reason it's called a late launch is, for one thing, it's happening after the system is boot, hence late. And it can be used to measure and launch absolutely anything. This is actually pretty cool. So the static root chain of trust, we start with the BIOS, boot block, that measures the BIOS, measures the bootloader, bootloader measures the operating system, and in theory, If you've got an operating system that supports it, you can use that to measure applications. So far, that last step only exists with some Linux extensions. And in fact, getting from the bootloader to the operating system requires that you have the right bootloader. Some support it, some don't. So you don't necessarily get all of this for free, but you can at least get partway there, and getting at least to the operating system is not too difficult. So there are some trade-offs with the static root of trust for measurement. The big pro of it is it's there, it's working, you just turn your machine on, and there you go. There are, however, some pretty big downsides to it. The first of which is, how much do you trust your BIOS? Do you know anything about your BIOS vendor? Do you even know which BIOS you're running? Has it been updated lately? So the measurements that are produced by the BIOS are extremely variable and cryptic. So even once you figured out do you trust your BIOS or not, making sense of it is tricky. And getting a BIOS manufacturer, even a trustworthy one, to tell you what they're measuring and how is very difficult. So there's no standardization yet, and some early experimentation has shown that two different machines that are both the same model, purchased on the same day, running the same BIOS version, will have different measurements of the BIOS. Yes. So when I say measurements is difficult here, and we need standardization, there's a reason for that. Yes. we were a little surprised by that too. There's a couple of potential reasons for that. One of which is that, and these are, I will note, hypotheses. Please do not take these as set in stone. Hypothesis number one. There are a number of things that the BIOS manufacturers are required to take into account for measurements, and there are others that are not clear. The BIOS measurements are supposed to reflect the state of the BIOS settings and the BIOS menu. Should you have a different measurement if somebody went into the BIOS menu, changed nothing, but saved it and left, or not? I wouldn't think so, but other people disagree, and the spec turns out to not actually be explicit about that. You got two different machines that both came from Dell on the same day from the same line, but Dell buys most of its components as generics. So two different machines that both look the same and have the same stats may actually have a different brand of graphics card, or I don't actually know very much about what's on the motherboard, but insert some motherboard components here because they have grabbacks, each of which may have slightly different communications protocols, slightly different, So if the BIOS is doing anything that directly reflects the actual components on the motherboard, those are going to measure differently, even though from a higher level perspective, we may not care. And if you have any insight into here, I'm not this low level most of the time. When myself and John Butterworth looked into a BIOS dump from two Dells that were differing, we found that there was a small value in the measured area which looked like a oh my gosh. They put a timestamp in it. Lovely. That would do it. Yeah, exactly. And this is why hashes are sort of, and probably because Dell outsourced the measurement code. Yeah. So that's part of what the standardization is looking at. It is looking at trying to make sure that little fragile things like timestamps are not included in a BIOS measurement, and that there's some kind of standardized way of saying which components are measured in which order, because of course that's going to matter. So there is work on regularizing this, but it's not there yet. The other big thing about BIOS is that there do exist things called bootkits. I'm not an expert on bootkits, but they do exist, and given that they exist, that's a major threat against the static root of trust for measurement, because depending on if the bootkit is in the second half of the BIOS, look, it's been measured, look, you can detect it, but if it's in the boot block, it now is your root of trust for measurement, and now you can't trust anything else in the boot sequence. Whoops. Yes. So this is why there are more things in the static root of trust for measurement. So the dynamic root of trust for measurement is noticeably more complicated. You have to send a special command to the processor, and the argument to that command is basically a region of memory. This command, sinit or skinit, senter, I'm not telling you enough here for you to run this yourself. There are some good books on the subject if you want to do it. When this mode is entered, all of the processing on this machine gets shut down, except for a special code module. A lot of the memory access mechanisms are turned off. The machine goes single-threaded. It really and truly closes down your machine. Anything that they could think of that appeared to be a threat to a small region of executing code is off. There is, if you look on the internet, you'll see, look, there's an attack on TXT. If you actually look at it, they say there's an attack, the fix already exists, and Intel was rolling it out at the time, and that's from like 2005. So they tried very hard to make this protected execution mode. So that little piece of code is part of the firmware. It's actually signed by the CPU manufacturer, and when it executes, the CPU verifies the manufacturer's signature on this little code module. And that code module is very simple and very dumb. All it does is say, you handed me a region of memory, and it hashes that region of memory and stores that hash in the TPM. Now, that region of memory can contain data and executables. But what this means is, unlike the BIOS version, where who knows what's in there, who knows what it's measuring and in what order, this is a very small, predictable bit of code, and I know exactly what I'm handing it. So I have control over how variable the input is, and this is actually potentially much more predictable. So once that region of memory is measured, it will pass control to it. Exact same principle as we had before, but now we're the ones deciding what's measured, what's executed. So we can now do a direct chain of trust from the CPU. We're not trusting mumble BIOS manufacturer in Taiwan here. We're trusting Intel or AMD's firmware, which is not necessarily perfect, but we at least have a much more concrete idea of who that is, where it came from. And this special code has its own locality. And I kind of hand-waved in passing earlier this idea of locality as permissions for the TPM. This is the one time that locality really matters. There are technically 5 localities on the TPM, 4 through 0. And locality 4 is only the DRTM. And there is a PCR that is only writable by locality 4. It is reset whenever the DRTM is entered, and only that locality can extend it. So if we see a value in that PCR, we know we entered secure mode, and the secure mode put this measurement in. Nothing else can do that. That's why locality is cool, is really for this. There is also, when it passes control to the region of memory, it then enters locality 3, which is basically things running in this secure mode. So we can now actually tell, this is what the tiny piece of code measured, and then we can follow a chain of trust up through whatever we're running. So this gives us the ability to constrain keys so that they can only be used when we're executing in secure mode. This gives us the ability to distinguish between things actually measured by the firmware and things measured by whatever the firmware launched. This is actually pretty cool. We call this late launch in part because some uses of this technology actually are launching NOS. So I can use this to launch an operating system or a hypervisor, but I can also do other things with it. So the chain of trust for DRTM is actually pretty darn short. This is an example for a virtualized system that launches from the DRTM. I've got the CPU manufacturer, which measures the I cannot change that lettering to white right this second. I'm sorry. What this says is the sign code from the CPU manufacturer, secure hypervisor, and virtual machines. Sorry, it was much more visible on the machine I created this on, and these are LaTeX slides, and I'm pretty sure this little machine here doesn't have LaTeX on it. And then that goes up to the applications. So here, we're using this secure mode to launch a hypervisor without trusting the BIOS at all. Everything that's happened before on the machine, it's over, it's done with. We don't have to trust it. We know exactly what the measurements of this first thing we launch are, and then we can use that to build trust in a larger system. So this is one use of DRTM that is really the late launch approach. And we could do this with a secure OS instead of a secure hypervisor, but I do a lot of virtualization work, so here you go. Here's the picture I usually end up drawing. Well, if the BIOS is bad, then it can stop you from going into secure mode. But somebody who's messed with the BIOS can't mess with your firmware.
Right, yeah.
Inherently. And even if they did manage to mess with your firmware, unless they've got Intel signing key, they can't make this look like legitimate Intel code. There is rollback protection in there to make sure that you can't install an old piece of firmware that may have an attack in it. But I'll be perfectly honest, I don't remember what that mechanism is. I believe I mean my CPU microcode, but I will be perfectly honest, I am not actually an expert in this area. I will refer you, if you actually care about the details of these components, to David Brawrock's excellent book, whose name is in your quick reference sheet under books, which has about 400 pages on the DRTM and related technology. Is the presence of a hypervisor required, or can the DRTM go from the sign code from the CPU straight to the OS and the application? This is merely one example. A hypervisor is not required. The DRTM can launch anything. And in fact, let me show you my next little slide here, which is a completely different use of the DRTM. Here, we're using the DRTM to launch not an OS, but an application. This is something called Flickr, and I have misspelled it. I always misspell it. It is Flickr with an E, not without an E. I'm sorry. This is a research project at CMU. Flickr is a research project out of Carnegie Mellon, where instead of thinking of the DRTM as a tool for launching you into a secure operating system, they think of it as a tool for secure processing for limited applications. So I will be running my generic Windows that launch from my generic BIOS, and I don't really care. It can be tremendously insecure, and my bank wants me to confirm an operation. You know, maybe I want to change my bank account. Maybe I want to sign something that says legally I agree to something. I will now launch into a Flickr code module that is a small single-purpose module that does something like, this code is signed with a Flickr document signing module, and it will use a key that is constrained to, or be signed with a quote that says, we are in secure Flickr mode. Flickr takes arguments, and basically what Flickr does is it says, I measure the Flickr code module and the input to Flickr. So that might be the document that I want to sign, that might be the first state of a document that I wish to change, that might be input to a function that I'm trying to calculate. It will also then extend a separate PCR with the output of whatever the Flickr module is. And now I can leave the secure mode. I just go back to my operating system. But now I have a record in the PCRs that I entered Flickr, I ran this code with these arguments, and I got these results. And those are all hashes. But I now have basically a reliable audit log that I executed specific code in a specific environment, which if you want to do something like bank operations, there's no way that my Windows can interfere with what happened when I was in Flickr mode. So this is a use of the DRTM that's completely different. In this version, you might be running the DRTM every 10 minutes with different code, potentially. But it's small and focused rather than using it as a chain of trust permanently for the state of the system. So the DRTM is very flexible. The signed code here is only just says I am here. Basically, this is the measurement code. This is how does the CPU firmware take a hash? You know, what are its, you know, how does it perform that operation? This is very minimal code. Beyond that, there are no constraints on what it can measure and what you can hand it.
So
The flicker scenario.
the flicker scenario.
In the flicker scenario, you are running a generic OS, which, as has been pointed out, could in fact be Windows or Linux. Flickr doesn't care. I was just using Windows as an example. Flickr doesn't care what OS you're running. There's basically two halves of Flickr. The part that says, I'm going to start the DRTM, and then whatever code you were running in secure mode. But once you're finished with your secure operation, you then leave secure mode and go back to whatever you were doing. This is just within the Flickr context. If I'm in this previous scenario where I'm doing something like virtualization starting from the DRTM, then I will turn back on things like multi-threading and various memory accesses, but I am not going to restore the previous state of the machine. The whole idea in this world, or if I were booting an OS that was not a hypervisor, is basically to bypass my trust in the BIOS and the bootloader. And all I am trusting them for at this point is to start the DRTM. And I can verify that it was started and with what code. So I, as a remote verifier, know for a fact you started the DRTM, here's what you ran with it, and I don't care what happened before that because it's gone. So, trade-offs of the DRTM. It has a lot of advantages. It is very flexible. It can measure anything you need it to. Executables, data, whatever you hand it, it will measure. And those previous examples were designed to talk about how flexible the DRTM is. It means that you're trusting the CPU, which, frankly, you're trusting anyway. I mean, it's your CPU. If your CPU is evil, you're really dead in the water. Not the BIOS, the bootloader, which is a lot sketchier. And your chains of trust tend to be a lot shorter. You are verifying the CPU firmware, the measurement code, and whatever you handed it, not the BIOS, boot block, and the BIOS, and the bootloader stage 1, the bootloader stage 2, and kernel. You know, this is a lot shorter to verify, and you have a lot more control over what you're verifying. But the big con is that this doesn't come automatically, and implementing this is in fact not trivial, as the people who are just chatting about having had trouble getting Flickr to work can probably testify. There's also one thing about it that's really mixed. The static root of trust executes once as the machine boots, that's it. The DRTM can be run multiple times. This is what makes Flickr work, is that I'm testifying to a specific operation done right. But if I'm using it for late launch, the fact that I can go into secure mode, log something, run indefinitely, leave secure mode, and then enter it again, all of my previous history is gone, including whatever might have happened in that previous launch. This also means that I cannot use both that secure hypervisor use of the DRTM, where I'm launching something into a secure mode, and something like Flickr, because the first time I run Flickr, all of my evidence that I booted into a secure hypervisor is gone. So, trade-offs, you can work around it, but you need to know that that's the case. So, those are the roots of trust for measurement. Any questions on those before we move on?